Out of the Fiery Furnace is brought to you by a company that makes aluminum for transportation, construction, and manufacturers of consumer products all around your house. Commonwealth Aluminum.
At least 10,000 years have passed since man began to use metals in their natural state, and perhaps 8,000 years have elapsed since he first began to smelt metals out of the living rock. But using the metallic elements was one thing. Understanding what distinguished one from another and why they behaved as they did, all this had to await the age of science. Less than 200 years have passed since John Dalton worked out the mathematical relationship of the atoms of matter and laid the foundations of modern physics and chemistry. Of course, there were theories long before Dalton. By the Middle Ages, many weird and wonderful notions about the source of particular metals had been erected on Aristotle's basic elements of earth, air, fire, and water. Those hopeful speculators were the alchemists. This was the world inhabited by the alchemists. In the vaults of their laboratories and among the flames and crucibles, they sought an explanation of their universe. The medieval alchemists devoted an intense effort to the study of the nature of minerals, and their fantasies and their concoctions were among the more obscure and uncertain additions to the store of human knowledge. The alchemists' muse was fire. Fire was the instrument with which they tried to force open doors to enlightenment. And they sought to use it as those alchemists of our own day and age, the nuclear physicists, have used the neutron to prise open the greatest doors which forever remain shut in the face of alchemy. The obsession of the alchemists was with the transmutation of metals, and in particular, the possibility of synthesizing gold. They had a central belief that in the molten fires beneath the Earth's crust, baser metals were constantly undergoing transmutations into nobler ones. In those satanic depths, they thought that lead became silver and silver gold. And it followed to them, therefore, that the aim of nature itself, ultimately, was to transform all metals into gold. And that was the process that they sought to master. And in doing so, they anticipated, they were fulfilling the very design of nature itself. The key word in the alchemists' vocabulary was transmutation. Gold was not simply a symbol of wealth. It lay at the end of a progression towards an elusive permanence, a utopian result. In those days of plague and pestilence, when life was measured in much shorter and more violent spans than it is today, the transmutation the alchemists sought was that from sickness to health, from old age to youth, immortality, the elixir of life. The lingering attraction of their preoccupations has endured into the writing of our own time, as with Jekyll and Hyde and Oscar Wilde's Dorian Gray. But it was a rainbow which always receded. No gold lay at the end of their endeavors, and the alchemists died poor. Their dreams were not to be realized until our own times, when the nuclear physicists began to investigate the radioactive metals and grasped the awesome knowledge of how to transmute elements not into gold, but into something more potent, energy. But first, the origins of the elements themselves had to be established. In Europe, the question of how the metals and other elements in the Earth's surface were formed and distributed, and in apparently such random fashion, continued to puzzle and perplex philosophers well into the 18th century. Only then did the obscurantist mists and clouds of the alchemist experiments begin to clear in the new enlightenment of the Renaissance. And then there began to emerge the first real insight and grasp of the nature of the Earth and its metallic ores and stones. And one of the most fundamental developments towards the discovery of a new science, geology, was taken in a city built itself strongly of stone, Edinburgh. By the middle of the 18th century, a group of brilliant and innovative Scots were all contemporaries and students in an environment of progress in scientific inquiry at the universities and other forums for the exchange and stimulation of scientific thought. Some of the most outstanding of them were, incidentally, pupils of one man. Neither his bust nor his portrait find a place here at Edinburgh University. But he was Andrew Plummer, the 18th century chemist, and he must have been a remarkable man in himself to have so successfully developed the curiosity and the talent of such a rare collection. One of his students was Dr. Joseph Black, who worked on the theories of heat, which established the principles with which were associated the development of the first efficient steam engine by Matthew Boulton and James Watt. And there was one other pupil of Plummer's whose theories, when they were first put forward, were branded as heresies, but which in the end became predominant. He gave to us the first real understanding of the nature of the planet we inhabit, and he laid the foundations for a new science of which today he's acknowledged to be the father. That science was geology, and his name was James Hutton. Hutton was an 18th century all-rounder, typical of his times. He had independent means, and he was in turn farmer, lawyer, physician, and chemist. But he was above all an observant and a curious man. Living in Edinburgh, Hutton's eyes and inquiring intellect turned upon the great rock which juts above the city, Arthur's Seat. He pierced the superficial commonplace that the rock was deposited in quite distinct layers, like a cake. His insight led him to see in this pattern an explanation of the rock's past. In the following years, Hutton, by studying and recording rock formations in various parts of the Scottish Highlands, constructed the coherent architecture of a new science. In 1785, he published a book, Theory of the Earth, in which he set out to interpret what he called the beautiful machine that constantly creates, wears down, and renews the surface of the planet. Hutton proceeded to give the first unified theory of the welling up of volcanic rock, its erosion and deposition as sediment on the ocean floor, and eventually its uplift once more by movements of the Earth's crust to form the sedimentary rocks we see all round us. It was this cycle that Hutton first began to recognize in Arthur's Seat in Edinburgh. Hutton's views were not at first accepted. His comment that in nature he found no vestige of a beginning no prospect of an end, was also far too heretical for a society which had yet to grapple with Darwin's theory of evolution. But by the beginning of the 19th century, and largely because of Hutton, the rocks were coming under more scientific scrutiny. As a result, Provence in the south of France came to play a role in a chain of events which in the end conceded an entirely new kind of metal. This part of France has a human history as dramatic as it looks. Called Les Baux, this rocky stronghold was a redoubt of medieval Europe. It dates from a time 1,000 years ago when perspectives were smaller and those who held and fortified this eyrie dwarfed all those who lived on the plain. We should be properly skeptical about the myths which surround discovery by accident, which is usually the reward of slow, painstaking steps from outmoded ideas. But the ally of all such discoveries is invariably curiosity, a keen sense of observation, and a willingness to get off the beaten track. And all those conditions were fulfilled here at Les Baux in 1821. A young chemist, who also happened to be an amateur geologist, called Berthier, was wandering through this famous chaos of rock formations here when he saw, just over here, something which was dramatically conspicuous in the white limestone hillsides. What Berthier saw was this stark red band in the rock. And he examined it, and he recognized it as being something in abundance which had been provoking and intriguing the scientists of Europe at that time. But it's the name that he gave to it which creates the link between this historic region of France and one of the important elements in the modern world. For Berthier named his red stuff after Les Baux. And bauxite, or bauxite as we've known it ever since, is the ore from which we get that metal which speaks perhaps most eloquently for our own times. The most common metal in the age of the common man, aluminium. Bauxite is still being mined at Les Baux. It's a simple operation as mining goes. However, the trail from Berthier's discovery of the first large deposit 150 years ago to the present was no straightforward path. No less than 1 part in 10 of the Earth's crust is aluminium. It's a staggering fraction. It's almost everywhere, and not just in the red bauxite where it's commercially available. No matter where you live, if you scoop up a handful of dust, the chances are it'll contain aluminium. So the question must be, why is it that this most abundant of all our metals, whose existence was deduced or suspected by scientists for centuries, was for so long undiscovered? And how was it that this most obliging of all our metals today was for so long so unyielding? The problem with aluminium is that it doesn't exist in a pure or native state. It's invariably oxidized. It's bound to oxygen with chemical links so strong that no normal method of smelting can reduce it to the metal we know. Until late in the 19th century, aluminium could only be separated from its ore by a difficult chemical process that made it extremely rare and valuable. In making this helmet for King Frederick VII of Denmark in the last century, the royal armorer would have found the aluminium for the base more expensive than the gold he used to decorate it. The new metal's rarity and soft silvery character reserved it at first for art and for ornament. Napoleon III was among the first to enthuse about one of aluminium's most useful properties, its lightness. He ordered the imperial crests on the standards of the French army to be made of aluminium instead of bronze, to make them easier for the standard bearers to carry. It was in these misty valleys, high in the French Alps, this is Saint-Jean-de-Maurienne, that aluminium from bauxite was first produced on an industrial scale at the end of the 19th century. The place was dictated by the requirements of the electrolytic smelting process. It needed huge supplies of the then new source of energy, electricity. Electricity in those quantities could at that time come only from power generated by mountain rivers. The discovery of this method of large-scale aluminium production was made simultaneously, but independently, by Paul Héroult in France and Charles Hall in the United States. What is called the Hall-Héroult process is still the basis of aluminium production all over the world. The basic reaction takes place in pots of molten chemicals, in which the purified bauxite is dissolved. When very large currents of electricity are passed through the pots, the aluminium is reduced and collects in the bottom. At intervals, it's tapped off, while fresh aluminium oxide is added to maintain a continuous output. Aluminium has been produced on a useful scale for less than 100 years, but already it's second only to iron and steel in its practical applications. The reason is its versatility. It has properties which combine the virtues of many metals. However, there's a price to be paid for extracting this remarkable metal from its ores, a staggering cost in electricity. Aluminium is the only metal to be smelted in this extravagant fashion. But once made, it can be recycled indefinitely. Aluminium is the child of the electrical age. It could not be made in quantity without prodigious supplies of power. The means of generating electricity was discovered in London in 1821, the very year that Berthier found the first extensive deposits of bauxite at Les Baux. At that time, the center of scientific thought and experimentation in England was the Royal Institution near Piccadilly. During the last 2 centuries, the names of those who've stood at this famous spot in the Royal Institution read like a roll call of the rise of science. Among the many famous and often historic demonstrations and discourses delivered here, few had the far-reaching consequences of 4 lectures on chemistry given between February and April 1812 by Sir Humphry Davy, who was then the president of the Royal Institution. Davy was not just an eminent scientist, but a brilliant lecturer, a man of great charm and vitality. And in this theater, he had created a large, new, and enthusiastic audience for science. Sitting up there behind the clock in 1812 was a young man of 21, a bookbinder's apprentice, the son of a blacksmith, Michael Faraday. Faraday had left school at 13, painfully aware that he could spell only very poorly, but an omnivorous reader of all the books that he bound, dedicated to self-improvement, and Humphry Davy was his hero. But were it not for a happy gesture, he had been given tickets to Davy's lectures by one of his master's customers. It seems wholly unlikely that Michael Faraday, bookbinder's apprentice, would have become anything other than Michael Faraday, bookbinder. As it was, he emerged from that apprenticeship an ardent and a passionate chemist. He made notes of Davy's lectures, and he sent a copy of them to the great man. These are the actual notes that Faraday took and which he bound. Humphrey Davy could hardly fail to be impressed. So impressed that he gave Faraday a job as assistant in the laboratory at the Royal Institution at a salary of 25 shillings a week. From that first step came momentous advances. Michael Faraday embarked upon a career of discovery which is unparalleled in the history of pure experimental science in the fields of chemistry and metallurgy. And in one particular field, he made possible the practical application of the most useful form of energy in the modern world, electricity. There was a widespread preoccupation with this newly discovered invisible force called electricity that could make sparks fly. There was awareness, too, of another mysterious force that powerfully attracted iron. But how closely these twin forces of electricity and magnetism were related, it was left to Faraday to discover and demonstrate. In 1821, in the downstairs laboratory of the Royal Institution, which incidentally has not changed since the time he worked here, Faraday set up this experiment. He had one of the early batteries and this apparatus, 2 wine glasses filled with mercury. In this one, a bar magnet stands upright and fixed, and in this one, the bar magnet is free to move. Above each glass, a wire. In this case, the hanging wire, which just touches the mercury, is suspended from a hook. And in this case, the wire or conductor is fixed. And wires from the apparatus, from the conductors and the glasses, come back to the battery. And then Faraday took this wire and completed the circuit. In this case, the hanging wire or conductor rotates around the magnet. And when he disconnected this one and connected this one, the process was reversed, and the magnet moves around the wire. So what you're watching is the principle which lay behind the development of the world's first electric motor. The principle of electromagnetic rotations, as Faraday called it, depends upon the reaction between the magnetic field and the flowing electric current. It's the basis of every modern device driven by an electric motor, from a food mixer to the starter on a car. But Faraday didn't leave it there. And for the next 10 years, he kept thinking about the relationship between electricity and magnetism. He had a great feeling for symmetry in nature and its forces, which he so passionately studied. And he was convinced that if electricity and magnetism could produce movement, then movement and magnetism should produce electricity. And in 1831, he showed this to be true in a demonstration which was even more significant. Faraday made his great discovery with an apparatus of elegant simplicity: a coil of iron wire and a bar magnet. Both are preserved at the Royal Institution. When Faraday took the bar magnet and moved it through the coil, connected to a galvanometer, there was a clear and unmistakable movement of the needle. Movement plus magnetism was producing an electric current in the coil. Faraday found that he could produce the same effect by rotating a copper disc in a magnetic field. The principle of electromagnetic induction, as Faraday named it, is the basis of all the generators which light the cities and drive the machines of the modern world. Michael Faraday's great mental exertions spread over more than 40 years produced discoveries which had revolutionary implications. They have put men everywhere in the modern world in the debt of the blacksmith's son. He opened a large new window which let in a flood of light upon new perspectives for all who followed him. His discoveries proved to be the point of departure for many of those practical, domestic necessities we now take so much for granted. The kindly, brilliant experimentalist was the first great luminary of the electrical age. Faraday was the first to demonstrate that electricity could be made to order. The man who gave it to the world was Thomas Edison. His laboratory is preserved intact with all its contents as part of the Museum of American Technology, assembled near Detroit by Henry Ford. It gives some indication of the inquisitive vitality of one of the key figures of the heroic age of invention. It's easy today to lose sight of the all-round contribution that Edison made to the easement of human existence. The Americans, who made a business out of almost everything, made a business out of invention, too. Edison, with his staff in his New Jersey laboratory, were the forerunners of that systematic, institutionalized research we have today. Thomas Edison was an Everest among the sandhills in the last part of the 19th century. His was an original, creative intelligence, one of the most prolific of minds, and over a career of strategic invention lasting almost 60 years, he took out over 1,000 patents. He became a genuine American folk hero. When he applied for a patent for this device in December 1877, nothing even remotely resembling it was found in what was by then the vast records of the United States Patents Office. This is Edison's phonograph. In their exuberant determination to master nature, the Americans conquered many things. In this instance, even death itself. Edison offered life after death with his resurrection of the human voice. Here, in a famous recording made on his phonograph in his 80s, is Edison's own voice. He's been dead now for more than half a century.
The first words I spoke in the original phonograph, a little piece of practical poetry. Mary had a little lamb, its fleece was white as snow, and everywhere that Mary went, the lamb was sure to go.
A straight line had led from Faraday to Edison. Edison, when 21, had read Faraday's description of the experiments with electricity. He confessed their inspiration. And it was in this field that Edison's own applied intelligence was to shine so brightly. In what he chose to do and how he brought his mind to bear, Edison was, par excellence, the inventor who conformed to the democratic ideal in America. He laid down a set of social and political principles for himself by which he determined what was to be considered practical and useful. The test of that was to be what the market would accept, and he made all his inventions answer that command. The electric light was Edison's, And the electric lighting system, as we know it today, was essentially Edison's concept. That was more than his invention of the world's first practical electric light bulb. In itself, a remarkable story of tenacity, will, and application. He tried literally thousands of materials, including a hair from the beard of one of his assistants, before he found a filament which would glow brightly in a vacuum when a current was passed through it without burning out. But Edison's great insight was into the potential of electric lighting, at that time available only in the form of dazzling arc lights, suitable for lighting large open spaces. And once again, the American mind wanted to democratize an idea. Edison wrote subsequently, "I saw that what had been done had never been made practically useful. The intense light had not been subdivided so that it could be brought into ordinary houses. I came home and made experiments 2 nights in succession. I discovered the necessary secret, so simple that a bootblack might understand it. It suddenly came to me like the secret of the speaking phonograph. It was real and no phantom." Edison restored a unity which the Almighty had kept separate. God divided light from darkness. Edison, for all practical purposes, made night the day. Within a year, Edison had worked out all the theoretical problems of subdividing electricity to supply large numbers of small lights, each of which could be switched on and off independently of the others. Where nothing existed, everything had to be created in his workshop. Dynamos, insulated cables, switches, fuse boxes, lamp holders, and meters. By Christmas 1879, he was ready to try out a whole system. The first private house in the world to be lit by electricity was this one, Sarah Jordan's boarding house, where some of Edison's employees lived. A new prospect was now within reach of millions, and a new role created for copper. Its softness and high conductivity made it ideal for electrical wiring. Henceforth, more than half the world's production of copper would be used in the service of electricity. Edison showed the way. Within 3 years, he fired up the first commercial city power station in New York. The Edison Electric Illuminating Company went into business on September the 3rd, 1882. 85 customers were wired up to the system. There were just 400 electric lights to switch on. But what a beginning it turned out to be. In that final quarter of the 19th century, industrial growth in the United States exceeded all previous experience. The mass production of machines, the new consumerism, the proliferation of steel-framed buildings, the spread of electric power and telegraph networks had aroused a demand for metals that traditional mining methods could not satisfy. The richer seams of all the metals had given out. The cost of recovering and treating poorer grades was rising. There were still vast untouched resources of minerals in the earth, but to exploit them, a new technology was needed. In the wake of the settlement of Salt Lake City by the Mormons, prospectors had found rich veins of gold and silver and copper in the surrounding mountains of Utah. What followed came to have a worldwide significance. In 1887, An entire mountain peak at the head of Bingham Canyon was found to be impregnated with copper. However, the grades were low, no more than 2% metal. While the mountain held millions of tons of copper ore, it wasn't worth the cost of sinking a shaft. For more than a decade, this huge deposit of copper, worth tens of millions of dollars in the sunrise of the electrical age, tempted and frustrated the miners. Then a young engineer, Daniel Jackling, changed the landscape of mining all over the world. Jackling's essential contribution was to envisage a wholly new dimension of open-cut mining on a vast new scale. It meant creating tools capable of moving mountains. Jackling's system was put into operation at the Bingham Canyon mine in 1906. He made a hive out of his copper mountain. Immense daily tonnages of ore were taken out of the pit by train through a honeycomb of tunnels. Over the following 30 years, the Bingham Canyon mine yielded metal worth nearly $1 billion. It's still profitable today, though the grade of ore is down to less than 0.5% of copper. But Daniel Jackling solved only half the problem of using low-grade ores. The other half was how to extract the metal from them cheaply enough. The next step was taken in several countries and began with a rewarding insight into the ancient processes of fermentation, as observed in an Australian brewery. It was to see in the way that rising bubbles carried impurities to the surface, the yeast of a new technology in mining. It was a likely accident that this should happen in Australia, where beer and mining were inseparable cultures, particularly in a famous mining city like Broken Hill. Mining companies at Broken Hill applied the fermentation phenomenon to the treatment of lead and zinc ores. They found that when air is blown through a soup of finely ground ore, the rising bubbles lift the particles of metal and leave the crushed rock on the bottom. The froth, in this case, was richer than the substance. The process was taken up on the other side of the Pacific, at Bingham Canyon, and found to work equally well with copper. Today, these flotation tanks at Bingham Canyon are a giant mineral brewery. It is this which makes the low-grade ores worth mining. And so it was that the industrial nations were able to surge into the 20th century on a swelling wave of production and with their raw materials assured by these Vesuvian eruptions out of the new craters all around the world. While the Americans in that last quarter of the 19th century were mobilizing their vast new resources of minerals and energy to launch the world into the machine age, the Europeans were laying the foundations for an even more radical transformation. Their resources were the intellectual powers of their scientists. In the old universities of Europe and the recesses of the human imagination, a wave of creative energy was forming which would take science to the threshold of comprehending the greatest mystery in the physical universe, the nature of the atom.
and of the awesome forces locked up within it. Like most great advances in science, the revelation began with the observation of some anomalous behavior in nature. In this case, the fact that some metals behave differently from others. By releasing a form of energy, no one could put a name to. The first steps in identifying and understanding that energy were taken in Paris.
One of the most emotional and contentious words in our language today is the term radioactivity. For many, it has frightening implications: nuclear fallout, the long-term contamination of the air we breathe and the things we touch, the threat of genetic damage to generations yet unborn. To others, it promises deliverance, powerful weapons against cancer and other diseases, a whole new range of scientific and industrial tools, renewable energy resources to replace those dwindling oil supplies. But what is beyond dispute is that the discovery of radioactivity in metallic elements like radium and uranium changed the world as we knew it. And the term radioactivity was invented by a woman who spent the later years of her life beside this quiet courtyard in the center of Paris. She worked in that rather ordinary-looking building over there, and one of the last things she did before she died was to plant that white rose. Her name was Marie Curie. She was the Polish-born wife of a French physicist, Pierre Curie, and for 60 years, 2 generations of the Curie family played a central role in the development of modern nuclear physics. Marie and Pierre, their daughter, Irene, and their son-in-law, Frédéric Joliot, all won the Nobel Prize. And it was their work, as much as anyone else's, that laid the foundations for the atomic age. Marie was working in Paris as a laboratory assistant in 1895 when she married Pierre Curie. She was looking for a subject for her doctoral thesis and became intrigued by Henri Becquerel's discovery in 1896 of mysterious rays emanating from salts of the element uranium. She began searching for other elements that gave off the same kind of radioactivity, as she called it. Her husband, Pierre, worked with her. He discovered that this radiation consisted of particles with 3 different electrical charges: positive, negative, and neutral. The great New Zealander, Lord Rutherford, was later to name them alpha, beta, and gamma rays. Here at the Curie laboratory, the nucleus had given up its first secrets. One's always surprised by the essential simplicity which in the end seems to attend so many of these great advances in science. It was using these crude devices that the Curies were able to measure the intensity of this radiation. And in 1898, they discovered 2 new radioactive elements, radium and polonium. In 1903, together with Henri Becquerel, Marie and Pierre Curie were awarded the Nobel Prize for Physics. And so by the beginning of this century, the door into the inner world of the atom had been prized open just a chink. Pierre was killed in a street accident in Paris in 1906. Marie carried on. In that year, she became the first ever woman professor at the Sorbonne. In 1911, she won a second Nobel Prize, this time for chemistry, for determining the atomic weight of radium. And then came the First World War. She and her daughter, Irene, explored the use of X-rays for medical purposes. Throughout all those years, they received large doses of radiation. In 1918, Marie Curie moved into this new office in the Institute of Radium in Paris, created largely as a result of her work. And it's been left pretty much as she must have known it, with her desk, her papers, some of her experiments, and some of her photographs. Irene also came to work here. And in 1925, the two Curies were joined by a young assistant, Frédéric Joliot. And a year later, in 1926, Frédéric and Irene, the Curie's daughter, were married. And in partnership, they took a new step towards that slow assembly of our picture of the atom. Frédéric and Irene began with the immense advantage of a large stockpile of highly radioactive material that had been accumulated for research by Marie. And by 1935, both son-in-law and daughter had won their Nobel Prizes for their achievement in realizing the dream of alchemists through the ages, the first artificial transmutation of elements. Frédéric Joliot went on to demonstrate in 1939 a new and potentially enormous source of energy, nuclear fission. His work was critical to the calculations that were to produce the first chain reaction in 1942, and later, the atomic bomb. Their record in the field of nuclear research notwithstanding, both Frédéric and Irene were excluded from the secret Allied wartime effort that went on to make the nuclear bomb because of their affiliations with the Communist Party of France. But they were the creative force behind the establishment of the French Atomic Energy Commission in 1945. That gave France an early entry into the nuclear field and enabled it to break the Anglo-American monopoly, first with the building of a nuclear reactor in 1948, and then eventually with France's own independent armory of nuclear weapons. Marie Curie herself worked on here until 1934, when her lifelong involvement with radioactivity finally caught up with her. 20 years later, Irene also became a victim of her great appetite for research and died from leukemia. Out here in the courtyard, where Marie Curie and her daughter Irene often sat, and where the rose that Marie Curie planted still blooms, we are still very close to the dawn of the atomic age. When Marie Curie died, her body was bleached by a fatal anemia induced by the overwhelming forces she had begun to unmask and to whose dangers she had unknowingly exposed herself over many years. This bloodless white rose might then be said to be a metaphor of the manner of her own death, and an allegory for the nuclear age whose awesome threshold she was among the first and most distinguished to cross. For ever since Marie Curie helped mankind put on the knowledge of the atom, she has faced us with its choices. The expectation of continuity and renewal, of which her rose in springtime is the happy reality, or should we fail to master the great forces that she began to liberate, the prospect only of the wasteland, the nuclear desert.
I'm Robert Raymond, and I'm the producer of this series. In this episode, we met two scientists who, although they worked in different parts of the world and in vastly different social environments, shared one overriding conviction. The scientists were Michael Faraday and Thomas Edison, and their shared conviction was that their work and their genius should be dedicated not to their own fame or reward, but to the general betterment of humankind. Their contributions to the development of the electric lighting system is an example. Today, however, it seems to many people that science and scientists are progressively removing themselves from the real world, that they're no longer so responsive to the needs of humanity, that we've even come, through science, to the point of putting our very survival at risk. One of the most determined attempts to come to grips with this problem is being made here at Pennsylvania State University, in a new curriculum, Science, Technology and Society. Its director is Dr. Rustam Roy, himself a scientist of distinction.
Well, my concern is that science is getting away from its connection with humanity, and that science, which was, as shown in your last series here, with Edison being concerned about practicability and usefulness as major criteria, that today we've totally lost that. And science is becoming a precious activity of the few. And I feel that's a very dangerous situation in which the public doesn't understand this magic, and it's kind of served up with certain quirky, interesting subjects and then told to pay the bill. So I feel that's a development which is much to be regretted and must be changed, especially when the public is paying $10 billion a year for just our curiosity. And I feel that situation will not last, and we must pay much more attention to the economy of the United States, to the environment, and make that a principal concern of the scientific community. It is no longer at all concerned about the economic and industrial base which supports the very work we do.
You mentioned $10 billion. What proportion of that goes on what you would call useful or practicable science?
Well, this is the portion that goes for what is called basic research. Our total R&D budget is about $100 billion, half from the public sector and half from the private sector. This $10 billion is given more or less for curiosity. Now, the unfortunate part is that the science community sells it to the public as being related to many useful things. But a very large fraction, much too large a fraction in my opinion, goes to jigsaw puzzle solving, to many fields such as particle physics, radio astronomy, all of which must be supported, but which perhaps are getting far too much emphasis in a country where our technology is clearly shown to be slipping, where the public science education is in a desperate state. I feel that the amount, the balance between science and useful science, just as basic, but useful basic science, has been grossly distorted.
Well, how do you think this change has come about? Where's the deterioration come from in a country which has been interested in practical things all its life?
Now you've got me, because you see, it's really our own fault. It is the fault of the science community. We were the ones that neglected science education. If the scientists were not concerned about science education, how can the public be concerned? And the budgets for science education, which were 50% of the National Science Foundation budget 2 decades ago, was zeroed out by Mr. Reagan, so that we allowed it to go down to nothing. So we have not been concerned about the public's understanding of the technology and science which they fund. We've let that go down. We have been the ones that have set the balance between useless basic science, or what I would say unconnected basic science, and that basic science which feeds what Edison said was practical and useful.
Even some of the great theoretical scientists like Einstein, I think, would have agreed with
well,
that.
Einstein, of course, was a master, and I think if good scientists would use him as a model, many scientists feel Edison was just an Edisonian crank that did a lot of good things, but nobody can say that Einstein was not the quintessential scientist. But very few people know that Einstein had a large number of patents, that he had many more patents for a major period of his life than papers. And you know what the patents were on? On refrigerators. Einstein in 1942 went down to the Navy and said, I'm quite a practical fellow. I know something about torpedoes. And the United States Navy decided where to put the engines in the torpedoes on the advice of Albert Einstein. Mr. Einstein was a union member. He always said, as our motto in this lab says, that concern for man and his fate should be the chief concern of scientists. He talked about labor, he talked about employment. Very few scientists today know the unemployment rate. They don't know what the deficit in the United States budget is. And I feel that every scientist who draws very generous sums from the public purse, should really get involved in the matters of technology and what is feeding him.
Well, what are you trying to do here then?
Well, we are trying to make sure that the technological literacy of the nation, through its school system, through its television, all of that, be improved very rapidly, because we really are a nation of technological illiterates. We are trying to work with the science community to let it clarify its own values. What are the values of scientists? Is basic science not properly defined as that which is closest to human need, instead of that which appears in some esoteric journal? So we are attacking the question and saying, within the community, what is basic science, what are our own values, and outside the community, in being concerned about the science education of the masses, not trying to teach them more physics, but saying, take a hold of your own fate.
Out of the Fiery Furnace is brought to you by a company that makes aluminum for transportation, construction, and manufacturers of consumer products all around your house. Commonwealth Aluminum.
The companion book, Out of the Fiery Furnace by Robert Raymond, is published by the Penn State Press and is available at bookstores throughout the country.